Okay, so in this lecture, I just want to talk real briefly about vector notation and conventions. I know some of you in this class have already had continuum mechanics or some other advanced mechanics class. Maybe you even covered it in your undergraduate course. Some of you are advanced graduate students. For some of you, this is your very first graduate class or certainly your first semester. So not everybody is starting from the same place with respect to their background in mechanics. So with that in mind, I just want to put us all on the same page so that you're aware of how I'm going to be referring to vectors and the types of conventions that I'm going to be using and that I'll expect you to use throughout the class. Okay, so let's talk real briefly about the kind of vectors that we're going to be using in this class. So in general, we're going to assume for this class, so I'll just say for this class, we're going to go ahead and use only the Cartesian coordinate system. Okay, we are not going to mess with any sort of curvilinear coordinate systems in general, at least not from a vector and tensor notation perspective. So once we've defined that, we can draw a Cartesian coordinate system. So it's just our three axes here. And you've probably referred to these as X, Y, and Z, or maybe if you go back to statics, you might say this is the I, J, and K direction. We're going to try to make everything more uniform and normalized and just call it the 1, the 2, and the 3 direction. And the Cartesian coordinate system is going to be comprised of 3 orthogonal basis vectors that will run along the axes. Whoops. So along there, we'll have a unit vector that we'll call E1 with a hat. So this is your first example of how I'm going to be referring to vectors. The underbar that you see here, that's going to be how I denote a vector, and the hat is going to be how I denote a unit vector, so a magnitude of 1. Okay, so along this direction, we have E3, the unit vector. And along that direction, we have E2, a unit vector. So that if I were to draw some vector, we'll call it V, and then I can project it in space. And okay, something like that. We could write just V as the linear combination of the magnitude in each direction, right? So we would write the vector V is equal to some alpha 1, which is the projection of V into the one direction, times the unit vector E1, which in the olden days back in your undergraduate career, you'd write that as I, plus alpha 2 E2 plus alpha 3 E3, which we could write more compactly as the summation from I equals 1 to 3 of alpha I EI. Okay? So now we want to find a more compact way to write this, because what we don't want to do is we don't want to be writing summations all over the place. So in order to do that, we introduce a particular convention called the Einstein Summation convention. So let's write that down, the Einstein Summation convention. And all that really tells us is that any repeated index implies a sum over that index. Okay, so let's go back here and write down this summation that we just had. So I equals 1 to 3 alpha I EI hat. So here I have an index of I and an index of I that are repeated. So in Einstein convention, that already implies a sum. So if I use Einstein, then I would write that as alpha I EI. And I drop the sum because the sum is implied by the repeated indices. Okay? So using that, I could then write my vector V is equal to alpha I EI. And usually we don't define the component in each direction with a separate letter. So I would actually write this as typically VI EI hat. So that VI represents the component of velocity in each of the three directions. Okay? Now, there's a couple things you should be aware of, things to watch out for with the Einstein notation convention. The number one thing is to say that that an index, whatever index it is, can only be repeated once. Okay, so what that means is that if I had something that looked like alpha I, beta I, epsilon I, well, now I've repeated the index twice, and that actually is not allowed. A couple other small definitions that you should be aware of, or just because I'll be referring to them. One is called a dummy index. And that's and I'll use that term to refer to any repeated index. So if I write VI EI like I just wrote previously, then I is a dummy index. Why do we say it's a dummy index? Because I can replace it by anything, and it means the same thing. There's nothing special about I. I could write that as VJ, EJ. It's equivalent, right? And I could choose any other letter I wanted. In contrast to the dummy index is what's called the free index. And it's a non-repeated index. And we're not free to change the letter of that unless we do it on both sides of the expression, both on the left and the right hand side of the equal sign. Okay, there are basically three ways or three formats for representing vectors. The first one is what we'll just call direct notation. And in the direct form, if we're looking at vector v, I'm just going to write it as v, a v with an underbar. And that means the vector v. I could write it a little bit more expanded, and that is called symbolic, or what I'll call symbolic. In that case, I'm going to write it as vi EI hat. So this is where I'm going to make reference to the basis vectors that are in play in defining the vector. And then the third way, which I'll probably use most frequently, is index notation, where I just write v sub I. So I'm only writing the components of the vector v, and it's understood that those are in the three basis vector directions. So that's the basis of vectors and the notations and conventions we're going to use. The next lecture is going to focus on how this extends to second order and higher tensors, as well as a few brief overviews of some important tensor quantities that I want you to be aware of.